So in this video, part 2, we are moving on to applying measures of variation. So variation is the single most important topic in statistics. The degree of variation in a data set is really going to help guide us on how much we can generalize the data and find reliable trends. So we've previously studied 3 main measures of variation: range, variance, and standard deviation. So we're going to revisit those and also talk about some variation on how to calculate these and going into more depth on these 3 measures of variation. So the first one is the range, and the range is a very simple calculation. We're taking the highest value and subtracting from it the lowest value, and that gives us the actual spread of our data points, right? So in this population A, so 3 populations, we have data on their weights. Data set A, we've got the lightest person weighed 40 pounds, the heaviest person weighed 60 pounds. So the range was 20 kilograms, I'm sorry, not pounds. In population B, we had the lightest person was 10 kilograms, heaviest was 90, so our range was 80 kilograms, a much bigger spread. However, if we look at the middle group, right, we had a lightest person of 10 kilograms, heaviest of 90 kilograms, and our spread was also 80. Our range is also 80. But the values between the smallest and largest value are very different in C than they are in B, and that's not captured by the range. So a big limitation of the range is that it doesn't give us any information on any other data point besides the lowest and the highest. So it's useful, it's simple, but it's limited in the information that it can convey. Now, previously, we also studied variance and standard deviation. Okay? And we're going to revisit those in just a moment. But I just wanted to remind us all of some important notation. We've done this in the past, that we have different symbols to represent different statistics when we're talking about our sample versus our general population. Okay? So if we're looking at the standard deviation of the sample, the notation is a lowercase s. When we're looking at the variance, the notation is s squared, right? Remember, because first we calculate variance with the square of all of those comparisons of each data point to the mean, and then in order to get standard deviation, we just do the square root of variance. Now, in terms of the population, the symbol is different. It's this Greek symbol sigma. So the population standard deviation is sigma, and population variance is sigma squared. So in the rest of these slides, if you see S or an S squared, we're looking at the sample standard deviation versus sample variance. And if you see sigma squared, we're talking about population standard deviation versus population variance. So let's remind ourselves what variance was. Variance is the measure of distance between each data point and the mean. And the way we calculate variance is we take each data point in our sample, we take each data point in our data set and subtract it from the mean. And each of those values gets squared. And that squaring removes any negative values. Okay? Because half the data points are going to be less than the mean, half the data points are going to be greater than the mean. So the half that are less than the mean, we would otherwise have negative numbers. So we square it in order to remove all those negative numbers. And then we add up all the values that we get. We add up all those squares, and we divide by the total number of data points. Okay? And so the equation looks like this. Variance of the population is sigma squared. Sigma squared is the sum of the difference of each data point x minus the mean squared. And then we divide that by the number of data points. And that gives us variance. Now there are some important properties of variance. The units of variance are going to be the square of the units of the original data. Okay. So if the original data was in feet, right, because you're looking at height, the variance is going to have the units feet squared. If the original data is seconds, because you're looking at time, then the variance will be second squared. Okay. So the units of variance are the square of the units of the original data. The value of variance can increase dramatically with the inclusion of outliers. So the variance is not resistant to extreme data points. If we include those outliers, if we include extreme data points, the variance is going to be greatly influenced by those extreme data points. Okay? Because we look at every single data point in calculating variance. And the value, finally, the value of variance is never negative. Okay? So we never get a negative number when we look at variance because we're squaring within the equation. So variance is only 0 if all the other data values are the same number. So if every data point was the same, then when we subtracted that data point from the mean, we would get 0. So sometimes we get variance of 0. That means that every single data point is exactly the same, and that tells us there's no variance. Okay. Now, standard deviation. Standard deviation is a very useful tool, very useful statistic. And standard deviation is simply the square root of the variance. Okay. And the standard deviation helps return the measure of dispersion back to the original units. Okay. So of the population, the standard deviation is the square root of the population variance. And so the variance of the population is equal to the square root of the sum of every data point minus the mean squared over the number of data points. Okay. Now, standard deviation has some important properties. Standard deviation is a measure of how much the data values deviate from the mean. Okay. So it's telling us very similar things as the variance. The value of standard deviation is also never negative, just like variance. And it will also be 0 if all the data points are the same. Okay. A larger number for standard deviation indicates a larger amount of variation in your data. And the standard deviation S of your sample can increase dramatically with the inclusion of outliers or extreme values. So the standard deviation, like variance, is not resistant to extreme values. And the units of standard deviation, or S, such as minutes, feet, pounds, whatever, are going to be the same units as the original data values. And that's really the advantage of standard deviation. It brings the units back to the original data. So when we're calculating standard deviation, okay, we have some procedures, some steps to take when we're calculating standard deviation. Okay. Number 1, we have to calculate the mean. Okay, because standard deviation is a measure of how far each data point is from the mean. So if we calculate the mean, let's say we have these data points, 84, 74, 50, 60, 52. The sum of those is 320. There's 5 numbers, so 320 minus 5 is 64.0. The next thing we do is subtract from the mean each individual data set, or rather each individual data point from the mean. Okay? So if we do that with each of those numbers, we subtract 84 minus 64, 74 minus 64, 50 minus 64, and so forth. What we get is 20, 10, negative 14, negative 4, and negative 12. The next thing we do is square each of those numbers, right? When we subtracted the data point from the average, we now square those numbers. 20 squared is 400, 10 squared is 100, negative 14 squared is 196. Notice it eliminated the negative number. 4 squared is 16, 12 squared is 144. Now we add up all of those squares, and we get here 856. And then we're going to divide by the number of data points. Okay? And there's a slight variation. Sometimes what you'll see is that they're dividing by the number of data points. Sometimes they're dividing by one less than the number of data points, or n minus 1. Okay? Here we are dividing n minus 1 rather than n. So if we divide 856 minus 4, we're getting 214. So 214 is our variance. 214 is our variance. Okay? But our standard deviation, we have one more step. We take the square root of that number, and it gives us our standard deviation. So square root of 214 is 14.6. And the units it was beats per minute, the original data, because this is pulse rate. So 14.6 beats per minute is the standard deviation. That is the distance between these values on average from the mean. Now, we have something called the range rule of thumb when using standard deviation. And it helps us determine something that's very important when we're doing statistical analysis. And a very important analysis is always determining statistical significance. And we'll learn a lot more robust methods for determining significance later in later sections. But this one is a simple, not super accurate, but it can be helpful method of determining whether a particular value in a data set is statistically higher or lower than the mean. Okay? The range rule of thumb uses standard deviation to determine whether any value in a data set is significantly lower or higher. And this rule is based on the idea that for many data sets, especially normally distributed data sets, 95% of the values are going to fall within 2 standard deviations of the mean. So any value in the data set is significant if it falls outside of 2 standard deviations from the mean. So for example, if we've got a population mean, right, that's mu, population mean, the 2 standard deviations below that mean and 2 standard deviations above that mean, any value is not going to be considered significant. But a value that is greater than the mean plus 2 standard deviations is significantly higher. And any value that is lower than the mean minus 2 standard deviations is going to be significantly lower. Okay. So if we take an example and we apply the range rule of thumb, let's use the pulse rate data. We have 153 pulse rates of males, and this is from Appendix B in your textbook. The average is 69.6 for this group. The standard deviation is 11.3. So we can use that mean and that standard deviation and apply the range rule of thumb to find the limits that separate a significantly high value from a low number, from a significantly low value. And now we can say, let's say we have somebody with a pulse rate of 100. Is that significantly high? So first off, let's find the limits. The average is 69.6, and the standard deviation is 11.3. Okay? So 2 times 11.3, that's 2 standard deviations, minus 69.6. Okay? That gives us 47 beats per minute. So any value in the data set, any pulse rate below 47 is significantly low. Now, for the significant high group, we take 2 times the standard deviation and add it to the mean, and that gives us 92.2. So any data point that is greater, anybody with a pulse rate greater than 92.2 has a pulse that is significantly higher. Okay. And the range of not significance is between 47 and 92.2. So a man with a pulse rate of 100 beats per minute, that is significantly high because 92.2 was our boundary. That was 2 times that was our mean plus 2 times the standard deviation. So that is a significantly high value. Okay. Now, when we talk about variance and we talk about standard deviation, these are statistics that are used to estimate the actual amount of variation in a sample or in a population. Okay. So whenever we're calculating a standard deviation or a variance of a sample, we're attempting to estimate the standard deviation and variance of the population. Okay. So S and S2 or S squared are estimators of sigma and sigma squared. Okay. Now, there is something called biased versus unbiased estimators. When an estimator does not systematically under or overestimate the population value, it's called an unbiased estimator. But when an estimator does systematically under or overestimate the population value, it's called a biased estimator. So the standard deviation of the sample is an estimator of the population standard deviation. And the way standard deviation is calculated, where we do the square root, that will always underestimate. Okay. So S, the standard deviation of the sample, will always underestimate sigma, the standard deviation of the population. So S is a biased estimator. Standard deviation is a biased estimator. On the other hand, when we look at variance, the way variance is calculated with the square, variance of the sample, S squared, does not underestimate or overestimate the variance of the population, sigma squared. So variance is described as an unbiased estimator. So that's always important to remember. Now, previously we talked about the coefficient of variation. Okay? The standard deviation is helpful to understand the degree of variation within a data set. But there are times when we want to compare the degree of variation between different data sets with different units even. So for example, comparing the degree of variation of the weight of all 10-year-olds in the state versus the degree of variation in the height of all those 10-year-olds in the state. When we're comparing variation between different data sets, it's helpful to use something called the coefficient of variation. This expresses the standard deviation as a percentage of the mean of that data set. And the way we calculate this coefficient of variation, we take the standard deviation, we divide by the mean of the data set, and we multiply by 100. So we're going to get a percentage. And that percentage tells us how big is that standard deviation compared to the mean? So if we take two samples of individuals, we've got a group of 25-year-olds, a group of 11-year-olds. We have an average weight in that sample 1 of 145 pounds, a standard deviation of 10 pounds. Sample 2, the 11-year-olds, the average weight was 80 pounds, but the standard deviation was still 10 pounds. So if we calculate the coefficient of variation, it's very difficult to compare the standard deviations of those two samples because they're the same value. It's 10 pounds in both groups. But if we look at the coefficient of variation, for the 25-year-olds, 10 divided by the mean, 145, times 100 equals 6.9%. For the 11-year-olds, 10 divided by 80 times 100 gives us 12.5%. So that tells us that the standard deviation for the 25-year-olds was 6.9%. 6.9 of the mean. And for the 11-year-olds, the standard deviation was 12.5 of the mean. So there's a lot more variation in weight in the sample of 11-year-olds compared to the sample of 25-year-olds. Okay? So that helps us compare those two standard deviations. If we do another practice for coefficient of variation, we go back to that pulse data of the males. If we have an average pulse rate of 69.6 and the standard deviation was 11.3, okay, then that tells us that the, let's compare, we want to compare what the variation is, okay. So let's say that, and then we have height. The average height was 174.12 centimeters, and the standard deviation of height was 7.1 centimeters. So let's compare the variation between pulse rates and heights of this group of males. So for the pulse rates, the standard deviation was 11.3 and the average was 69.6. 11.3 divided by 69.6 times 100 is 16.2. For the height, the standard deviation was 7.1 centimeters divided by 174.12 centimeters, the mean, times 100 is 4.1%. So we can see that in this group of 153 men, there was a lot more variation in their pulse rates compared to their heights. 16.2% coefficient of variation for the pulse and only 4.1% in the height. So that helps us compare the variation.